I've been obsessed for the past 10 years with what makes for clarity and truth in visualization. And sometimes the best way to define something is via negativa. You define what it is not. So although it's difficult to define clarity, it is relatively easy to define clarity as the absence of distortion. And that's going to be the subject of this talk. I want to start with a provocation, and that is, what if I told you that you cannot see data? You can only see its projection through a series of distortive lenses. And that is not only the theme of this talk, but we're going to put that on mathematical foundations. And I'm going to prove that theme to you that I just spoke today. And as with most good research and application, I will be standing on the shoulders of giants. So you will see citations throughout my talk to papers. At the end, there'll be a full bibliography. But I want to call out in particular this framework that I'm going to use from an InfoPhys paper that appeared in 2014 by Kindelman and Scheidegger, and it's called an algebraic process for visualization design. And if we want to be clear about things, the ultimate language of clarity is mathematics. So there is math in this talk, but first I'm going to start with examples so that things can be as clear as possible. All right, so there are three characteristics of a visualization that is true or is undistorted. And these are the beauty of these characteristics is that these are not heuristics. These are actual mathematical properties. And you can see them in order. And first, I want to talk about invariance. Okay? Invariance has a very simple definition. And it says that the same data always produces the same visualization. This seems very obvious, but I'm going to show you half a dozen violations of this principle from New York Times Graphics and other well-respected houses. So let's start here. Okay? And the point I want you to gather from this graphic is that the underlying data in both of these graphics is identical. There is absolutely no change in the data, but they leave completely different impressions on the viewer. Okay? So the only thing that is different between the graphic on the left and the graphic on the right is the ordering of the entities. And these entities are countries. They belong to a set. Sets generally don't have an ordering. But by changing the ordering of the countries, you change the shape of the visualization, and as a result, you change the shape of the concept that people grok from the visualization. Let's look at some more examples. Same precise, exact underlying data in both of these visualizations, except it looks like one is dominated by pickups and the other is dominated by drop-offs. Same exact underlying data. The only thing that has permuted is the order of the data, and we're going to explain why. I'll show you how we can fix all of these issues in just a minute. Here again, same population, two different density samples from the same population. Now, looking at these, you would not guess that both of these samples are drawn from the same population. They look like they're from totally different priors. Hedgehog plots. So here we are visualizing a vector field, which is a common operation in scientific visualization. And the plot on the top and the plot on the bottom are plots of the same underlying population, the same underlying distribution, but they look totally different. And if you look at this and try and get an intuition about what's happening in the vector field, your intuition will be wrong. And what we call this is a hallucination. So a hallucination is what you get when there is a failure of invariance. This is a failure of invariance. And this is the same data produces different visualizations. And you'll realize in mathematics, this is when we call a mapping or an operator ill-defined, right? So you have the same pre-image, which results in two different images. And this would not be a function. All right, so let's look at how to fix things here. So on the top, we have the hallucination. And on the bottom, we have the invariant version. And what I want you to notice about the version on the bottom is that not only is it much clearer, but the position of the data is completely decided by the data itself. So no matter how I permute the countries in this equation, they will always map to the same physical location because the location is completely determined by the data. Does that make sense? Is that clear? Okay. It's also much clearer because now what this is trying to show is differences between the genders. And now with this line that we have at a 45-degree angle, we can see what equality would look like, and we can see how much each of the countries vary from equality. All right. So again, hallucination top, invariant visualization on the bottom. Does anybody have a guess? So remember, all three of these graphs are visualizations of the same data. Does anybody know why this is happening? Any guesses? Yes, so that's right, and we're going to go deeply into that. It has to do with the points overlap, but if you really go into this, it is because the semantic that we are trying to visualize is commutative, but compositing is not commutative, okay? So whether somebody was picked up and dropped off in the same location or dropped off and picked up in the same location, it doesn't matter. It's the same group of people. But compositing, at least the over operator from Porter Duff, those of you who know that, is not commutative, okay? And now this is obvious when we use opaque glyphs. It's really obvious that yellow, well, A over B in the first on the top row and B over A are different. It's really obvious. It is considerably less obvious when you use translucency. So there's a 50% alpha channel on all of these objects here. How many different classes are we trying to represent here? Yes, there should be 3. But there is a 4th hallucinated class, and that comes from the fact that even with translucency, compositing is not commutative. And if you actually look at these 2 colors side by side, they are completely different. But they are trying to represent the same set, and that is a hallucination. How many people out there use scatter plots? Okay. How many people use scatter plots with translucency? Most of them do. So you have a combinatorial number of hallucinators in your visualization as a result of this. Okay? So we're going to talk about a few ways that you can actually overcome that. So one is use a commutative blending function. Okay? So additive blending, for instance, is commutative, and rendering order doesn't matter. That can give you some perceptually funky results, though. The other alternatives are to use a custom blending method or proper sampling, which is what we saw in the third and bottom invariant diagram. And I want to talk about these things in a little bit more detail. This is from Mayorga and Gleicher, 2013, their splatter plots paper. So this allows you essentially to take a dense scatter plot visualization, and then do an abstraction over that, which removes the number of hallucinators. So on the far left, you will see that blue hues, if we just use naive RGB compositing, blue hues tend to dominate. Okay? And what that means is that in the areas of overlap in that diagram on the left, you will tend to think, although it is not true, that the intersections belong more to the blue circle than to the other 2 circles. Okay? So if we use a perceptual color space like LAB and ensure that the intersections have maximal distance from one another, and then far right attenuate the lightness, we get better results and fewer hallucinators. Okay? There's a lot more in the splatter plots paper, but I wanted to give you a sense of how you can remove hallucinators from your visualizations and your scatter plots in particular. This fix is relatively easy. So notice we have the hallucination on top. And on the bottom here, although the diagrams are not identical, they're not fully invariant, you could look at the density plots on the bottom and believe that those 2 distributions are roughly the same. Does anybody know what was done here? So the samples are different, but the underlying distribution is the same. So this is just kernel density estimation, and that gives you an estimate of what the underlying probability distribution function is. So your visualizations show the same shape, even though they're different samples. Make sense? Okay. So hedgehog plots here. So what we're getting at the top in the hallucination is something like a moire effect. Okay? So the sampling grid is regular. And like, you know, when you look at images through a screen, they kind of start to swim. Or if you look at a computer through a screen or you take a picture of a picture, that's a moire effect. And on the bottom here, instead of sampling at regular points, what Turks and Banks recommend and what they've done is they reconstruct the underlying vector field. And again, these techniques are not that important. What is important is that you see for your particular class of visualization problems that there's a way to remove your hallucinators and remove your confusers, which we'll talk about in a second. And here they instead optimize for relatively uniform placement of glyphs, and it's much clearer. There's no hallucinator, and you have invariance shown at the bottom there. So we talked about hallucination as a failure of invariance, and hallucinators are the data points that cause hallucinations in your visualization. The question is now, how do you find hallucinations? And the answer is that you provoke your data. You sample your data, you permute your data, and you see if your visualization changes. That's the key to finding hallucinators. Okay, so we're on to unambiguity. And it's, again, a very simple principle, which in practice is violated many times. So unambiguity says that different data always produces different visualizations. And so now we're going to look at cases where there's 2 or more in the pre-image and only 1 in the image, 1 visualization in the resulting image. All right, so color blindness is a really classic example, right? So in stimulus space and in data space, I have 2 distinct data points, red and green here. When you map them into tristimulus or bistimulus space, right, for people who have deuteranomaly who are missing a cone, you're going to see that the same stimulus, or sorry, 2 different stimuluses map to the same percept. So this is a lossy mapping, right? I have 2 different pieces of data, but when it hits somebody's retina, it's smashed into a single piece of data. So here's confusion in machine learning. And so this is from a deep neural network that Google created, which was trained to recognize dumbbells. Okay? And what you'll see is that this classifier is actually confused about the difference between a dumbbell and an arm. And this means that you can throw an arm at this classifier or a dumbbell at this classifier and get either a false positive or a true positive out of that. So computers can be confused too, and computers can hallucinate as well. So this is bas-relief ambiguity. And what I want you to get from this visualization is that as you see on the far right, in the column on the far right, all of the geometries in this picture are substantially different. All the geometries are distinct. However, from a certain perspective, they all render exactly the same. And the reason is that every geometry skew has an offsetting lighting transform. And therefore, even though all 4 of the rows of geometries that you see on the left are different, they look the same to the viewer. Okay? Now, does anybody work with machine learning data? Okay, so many of you will be familiar with tensors. And the idea with tensors, whether you know what they are or not, doesn't really matter. You have these high-dimensional objects. And we want to then project them into 3D and ultimately onto a 2D screen and see what they look like. And the confusion that's going on in this visualization is that you have very different tensors which produce very similar-looking visualizations. We'll see how to fix this in just a second. Okay? Again, tree maps, how many people are familiar with tree maps, right? So there are multiple tree maps that can produce this, there are multiple trees, multiple data that can produce this exact same tree map. Parallel coordinates, same thing. Different data sets, same parallel coordinates plot. This is a streamline visualization. You can have 2 different streamlines with different velocities, and they'll map to this exact same visualization. So what we've seen here is confusion, and this is a failure of unambiguity. And this is when 2 distinct data points, instead of mapping 2 distinct visualizations, map to the same visualization. So let's look at how to fix that now. All right, so if you use superquadric surfaces on the bottom, instead of having this lossy mapping where you cannot really see how different the tensors are, it's the same data set underlying the top row and the bottom row. It's just that the top row has confusers in it and the bottom row doesn't. So you're using a dimensionally appropriate representation of your data to get something that is free of confusion. And we'll see that confusion as a whole is very often about loss of dimensionality. Okay, so here for tree maps, same thing. And what the cushion tree maps do on the bottom is they have a lighting function which changes depending on the rank of that node in the tree. Okay, so the lighting here in the bottom is adding this missing dimension, which was how high was this node in the tree. And now we have 2 different trees, 2 different data sets that in fact produce an unconfused or unambiguous representation, 2 different visualizations, right? Same thing, it's really simple with parallel coordinate plots. You can see that the data or the coordinates on the left do not have a twist, they have a twist to them, or kind of like this upside down V shape. And then the data that is on the right is relatively straight through, right? So again, we have removed the confuser and we have an unambiguous representation. Here again, on the bottom, using line integral convolution with contrast, now different velocities, in fact, look like different streamlines, right? So even though the path is the same, you get 2 different visualizations. Is everybody following me? Or is this boring? Is this interesting? I'm curious. Yes? No? How are we doing? Okay, good, great. All right, so confusion, right? So different data produce the same visualization. And let's look at antidotes to confusion. So I mentioned earlier that confusion is often about loss of dimensionality in the representation. And here's the beautiful thing, and it's true about all of the properties we're going to look at in this talk, that confusion can occur at the human level or at the machine level. And there's this beautiful parallelism we're going to look at as we develop this further. Okay, so the third category, or the third property, is something called correspondence. And the idea behind correspondence is that you have no confusers and no hallucinators. So you've already shown that your visualization is invariant and unambiguous. And now you have something that looks like homomorphism, which says meaningful changes in the data lead to meaningful changes in the visualization and vice versa. So this is a structure-preserving mapping, and we say that the data and the visualization have a correspondence if you have no invariance, if you're invariant and unambiguous, and you have this correspondence that I've outlined just here. So this is, in some sense, a super property of the further two, because in order to have correspondence, you must also have invariance and unambiguity. Okay? So let's look at this here. So what are we looking at? How many people use force-directed layouts, or D3? Anybody use D3? Okay, so yeah, force-directed layouts are cool, and they look really fun, like molecules moving around, but they're very unstable. And by unstable, I mean that you can have the same or similar networks and get totally different visualization results out of them. Okay? So what we see here is that in the data on the left, we have fewer edges. We add a few edges, and the addition of those edges isn't really reflected in the visualization. I'm going to show you a properly correspondent version. So what force direction, if you do it naively, does not preserve is the rank of the node in the graph, right? So if you topologically sort this graph, A will always come out on top. But in the non-correspondent version on the top, A's position isn't really preserved in any meaningful way. So what we do in the correspondent version on the bottom is that we make sure the representation of the graph, even you can do force direction kind of within each of the rows there, but we make sure that it's topologically accurate. Right? So this means that when we now add edges to this graph, the visualization will preserve the rank of the nodes, and you can still topologically sort them, if it's a DAG. Okay. So we've been playing fast and loose with some of the mathematics, and we've also made this very naive assumption that visualization is the process of going from data to marks on a screen. But visualization is a lot more than that. So I want to sharpen up the mathematical foundations of the talk, and I want to show you a broader definition of visualization. So we have a universe of things in the real world, right? We select some things from that universe. That becomes our set of data. That is then turned into a representation that is compatible with a Turing machine. That Turing machine then produces an image on a screen, and that image then produces an impression in someone's mind. So this is a really deep series of stacked lenses, and they can all be modeled very precisely and mathematically. And at every one of these positions, you have the possibility of distortion. Okay? So I want to talk about each of the mappings in detail and talk about the types of bias that can enter at each point. So at selection, how many people are familiar with cherry picking? Right? So cherry picking, sampling error, algorithmic bias. We're going to talk a lot about algorithmic bias. That's kind of the hidden theme of this talk, so we'll come back to this. Okay, so when we move from the universe to data, who made that decision? This is editorial, this is curatorial. And sometimes the most interesting data is the data that you never get to see. And it is never even in the data set because somebody decided that you don't need to see that. When we move from data to a representation in a computer, this is where we see floating point error, sampling errors again, loss of dimensionality, right? Because we're going from a world which is 4D at least, to maybe a three-dimensional vector in a computer, to a projection on a 2D screen. There are so many things that can go wrong there. And of course, tractability bias, which is computers ultimately are only a model for things that are happening in the real world. And it's very easy to solve a computationally tractable version of whatever your real data problem is when you're modeling. That's what modeling error is all about. Finally, and I invented this horrible word, graphicalization, because I didn't want to use visualization very deliberately. And this is basically the process of going from an image, going from a representation to an image on a screen. And here we have limits of resolution, color gamut. Everybody has been trained to hate pie charts and rainbow color schemes by now, is that true? For continuous variables, great. So what's interesting to look at, if you look at pie charts here, it's actually an addition of a dimension and not a loss of dimension that's causing a distortion. Because what you want to visualize with a pie chart is unidimensional data, but a pie chart is two-dimensional. So you have this extra degree of freedom which causes this distortion. And then finally, there's perception and cognition, which is by no means trivial. Okay, so we have disabilities such as color blindness. How many people have heard of metamers? Okay, so metamers are colors in the real world which have different spectral distribution, but when you map them onto the retina is confused and they look identical. Personal bias, like this is a whole another huge one. We'll talk about this a little more in a second. And perceptual limits, like what's the resolving power of the eye? What color gamut can you see? Okay, so this whole thing deserves to be called visualization. Okay, and the real title of my talk, which I didn't use because I don't think anybody would have come, is this. Visualization is a composition of mappings from the real world to the mind. Mappings can be lossy and opinionated, so fix your mappings. That's really what the talk is about. And let's go a little bit deeper into the mathematics here. Okay, so stay with me. How many people like math? Oh, cool, yay, fantastic. That's why I'm speaking at Strata, great. So even if you don't like math, I'm gonna try and give you an intuition for how this works. Okay, so we've been talking about this mapping from data to representation to image, okay? And now, we saw earlier that visualization can sometimes be sensitive to changes in the underlying data. And we said that correspondence was when meaningful changes in the data produced meaningful changes in the resulting visualization, okay? So this is trying to be a commutative diagram. And alpha and omega are the endomorphisms or symmetries on the left side on your data set and on the right side on the actual image. I'm gonna give you an example in just a second, okay? But what's interesting about this is that now we can use computers to give us a sense of which visualizations are true and which visualizations are not. And this is extraordinarily important, right? So what you need to get out of this diagram is that this orange line you see here represents the set of things in a given data visualization pair that make this diagram commute. And that bijection is precisely the set of things which are true and undistorted in a visualization. So you can pull back from the image or put to the data or push out from the data to the image. And these are things that are preserved in this round trip from the image to data and back, okay? And the idea here, let's take an example of an alpha omega pair, okay? And remember that to have correspondence, you already have invariance and unambiguity. And I apologize, I know this is complex. I had to read this paper like 5 times myself. I know it's dense, but I'll make the slides available, and I encourage you to read Kindleman and Scheidegger. So the important thing, I wanted to give you intuitions for what correspondence looks like. Correspondence consists of alpha omega pairs, okay? And here's the thing, alpha is a meaningful transformation on your data. So let's say that you are visualizing scalars, okay? And you now negate all of those scalars. If your visualization has proper correspondence, there should be a corresponding omega function, which is a symmetry on your visualization, which negates the colors that you see. And if you know a little bit about opponent color theory, red and green are in opposition and blue and yellow are in opposition. That just gives you an intuition for what correspondence really is. It's alpha omega pairs. And the important thing to get from this diagram, if you get nothing else, is that we now have the foundations to have computers help us reason about what is true. And this is extraordinarily important, right? Visualization has felt like this really arbitrary process. This fiber product is what you call this pull back or push out. It's a set of things that make the diagram commute. But visualization has felt like this really arbitrary and mysterious process where you need a designer, and why is this design right, and I don't know. And I think we are very close to a time. I don't claim it's tractable. I don't claim it's easy. I think we're very close to a time when we can use computers to tell us where the distortions are in our visualizations. And it's all based on the fact that we have mathematical footing for what is happening in the visualization. And going from data to an image is not the same as, but is a proxy for selecting something out of the universe and mapping it into the human mind, which is the real problem that we're faced with in visualization. So I want to talk a little bit more about algorithmic bias. So we saw this first mapping function was selection, okay, moving from the universe to data. This is editing, this is curating. And I think there are some real shockers to be seen in this department. And I want to start, how many people everybody uses Facebook, true or false? Yeah, for better or for worse, right? So who decides or what decides what you see on Facebook? The content ranking algorithms. They are trained by you and by your interests, but they are not transparent to you. Who decides what you get when you run a Google search? The content ranking algorithms. They are trained by your interests, but your interests are not transparent. How the algorithm actually functions and what its biases are not transparent. And I'm going to show you some examples here in just a second. So has everybody heard of pareidolia? Right? So pareidolia is when you see patterns where there is nothing. So this is Jesus and a piece of toast, if you didn't see him already. And it's a very common phenomenon. And it has to do with the fact that the eyes and brain are pattern recognition machines. And what I'm going to show you is that algorithms can have pareidolia as well. And this is why Deep Dream has been so fascinating, and Inceptionism in particular has been so fascinating. And the intuition for this is if all you have is a hammer, everything looks like a nail. right? So we are walking around, and the algorithms are walking around with a set of priors or a set of a priori biases for what is important and what is not important. And the same way that when we were kids, we like to look at clouds and see birds and see cotton balls and see all different kinds of things, using inceptionism, neural networks can hallucinate. And that is and they can be confused, and that is what this image on the right is all about. The prior here, the input here is an undisrupted cloud image. Okay? But when you keep feeding this to a neural network and asking it what it recognizes and which features it thinks are important, it starts to emphasize certain things and quote unquote see objects that are not really there. Right? So here you can see that this one must have been trained to recognize some mixture of pagodas and fish. And we mentioned the law of the instrument, or Maslow's law, earlier. And what I want you all to consider is that we all have interest-colored glasses, and we're wearing them all the time. Right? And the same is true for the algorithms. Right? So there is no pagoda in the image top left. But if you keep coaxing the neural network with this data, it will eventually say, yeah, I see a pagoda there. Right? And this is what the idea fix is all about. Right? There are things that we are all individually obsessed with and interested about. And the same is true for algorithms, and that governs what you are able to see. So my question for you is, what are the lenses that you are wearing? And what are the lenses of the algorithms that are feeding you the content that you think is interesting? Right? And so my real call is that we come up with a form of inceptionism, and I'll explain what that is in just a second, for all of our content ranking algorithms. Okay? And this does two things for us. It allows us to assess the difference between the algorithm's importance ranking and our own, and it's a fascinating way to know our own biases. So in the Facebook feed, as one example, or in a Google search result, they will show you things that they think are important to you, which may or may not be important. And there may be things that are important that they don't show to you. This is the whole idea. And what we're doing with inceptionism, and I want to be clear, in all cases of inceptionism, we won't necessarily get an image out the other end. But what is happening with inceptionism is that we take loosely structured or semi-structured data, keep feeding it to the algorithm, and ask it what does it notice. And eventually you get these really strong hallucinations. And that is a really good indication of what the a priori bias of that classifier is. And you're using this stuff every single day. This affects what you see on Google. This affects what you see on Facebook. And there's this really tenuous and strange loop between what you like. OK, I liked something on Facebook. Well, that's going to influence what I see. And then what I see is going to influence what I like. So we are training these algorithms in an individual network of interest, what our personal biases are. And here's what's super interesting. What would you pay to know what your personal interest or your personal colored glasses look like? What would you pay to see the digital projection of your interests or your personal distortions? And the answer is we pay billions of dollars. This is why advertisers flock to Facebook and Google, because they can sell into what your biases are. Right? So transparency in algorithms. It doesn't mean the algorithms are bad. We are training them with our behavior, but we need to see what their a priori biases are so we can have better algorithms out the other end. So big picture. Visualization is the process of selecting data from the universe, representing that in a representation that is compatible with a Turing machine, taking that and displaying it as an image and forming an impression in someone's mind. The orange line there says, most importantly, that we can use computers to detect what is undistorted in this process of transferring from the world into the mind. And that's all I wanted to say. I'll make these slides available online. These are the papers and inspiration for the talk. I want to thank Steve Harose, who spent some time kind of going through this crazy talk with me and turned me on to the Kindleman and Scheidegger paper. Kevin, my co-founder. I haven't written any code this week. I've been a bad co-founder. Alistair, who invited me to speak at Strata, and my mentor, Richard Stark, in algebra. So please stay in touch. Check out our product. I didn't talk anything about what we do, but it's a social database. And I would love, do we have time? Yeah, we have plenty of time for questions. I'd love to talk more. Thank you. Hi.
I think of good visualizations as a combination science and art.
Yeah.
Where does the artist, where do the aesthetics come into your view?
This is a great question. And the chances of me coming up with a pat and correct answer are pretty slim, but I'm going to take a shot at it. Oh, the question, yes. The question was, visualization is both art and science. And where does the art come into this? I like Knuth's definition of art and science, and he said, science is everything we can explain to a computer, everything else is art. So I think the best answer to your question is, what's left when we compute this fiber product? That's still interesting and still aesthetic is where the humans are going to play. And I don't think, it's kind of like theorem provers in mathematics. They never really panned out. But the aesthetics come where there's no clear distortion, right? There's no clear confusers, clear hallucinators, clear lack of correspondence. Then you can play with aesthetics. Best I can do with that. Yeah? Hmm.
Choices to trim out things that are relevant and basically dumb things down so that you're manipulating people looking for what you want.
Yes.
You seem to be going in exactly the opposite direction.
Yeah.
Am I interpreting that correctly?
Yeah. So let me repeat the question. So the question is that he has been taught visualization as a form of storytelling, and storytelling has a point of view. And you are encouraged to edit things out and to tell the story and lead the reader to the conclusions that you want them to reach. I think telling a story is important, but having an agenda and being honest are fundamentally different things. And I think, and we've totally lost that. There's hardly any journalism left in the United States or in the world, right? So journalism, in David Brinkley's definition, is you tell people what happened, and if you know why it happened, and anything more than that is not journalism. And so it depends on where you want to fall. Like if you're building visualizations that are for advertising or some kind of agitprop, then yeah, like you really need to be selective and you need to tell the story you want to tell. At the very least, we can at least document what we didn't include in the visualization. I think that's the shortest answer I can give to, and we have to be honest, it's not good science. And look how bad reproducibility is in science right now. It's for the same reasons, because people think science is journalism too. And they're like, oh yeah, well let me not include all these results. That's why nothing is reproducible. Or so few things are reproducible. Their physicists are still doing okay. Yeah? Let me back up. So the question was, how does he know that the objective interpretation ends at the image? How does he know that all of the minds interpret the image in the same way? We don't. And that's why there's a box drawn around this core central data representation image. The best we can do on the mental side of things is usability studies, perception studies, what we know about disabilities. But no, it's extraordinarily difficult. I mean, that's why I didn't go for, hey, the fiber product is a set of things that are in the universe and also in the mind, because it's really soft. Anything else? Great. Well, come by, say hi. Happy to talk to you after the talk. Thank you so much.